Welcome 1200. What we are doing is the Balmer series and the ground state of the hydrogen atom today. Now, what you are to do is determine the wavelength of certain light that you'll be viewing in lab today. And well, it's going to be that from the hydrogen and helium atom. So what you'll do with that information is find the ground state of hydrogen and also a certain transition that occurs in the helium atom. But wow, that's for your analysis. I should just stick to how you are to acquire this data. So I'll do that. Let's see. Spectrometer. This is the instrument we'll be using. There's a picture of it in your lab manual. And in that diagram that you have, it points out and lists the different aspects of this that allow it to function. In fact, let me put you on pause and bring you closer so we can briefly go over this here. So hold on. So here's our spectroscope, and what we do is we shine light in this region here, and it goes through this culminator. And essentially all that is just like this little narrow slit that allows light into it. And there's probably like a little system of lenses in here that ensures that the outcoming light is all parallel. The rays are parallel. It's in a nice straight direction, and it hits our prism located in the center here. Now, once the light goes through this prism, it is diffracted. So diffraction occurs at 2 points. Once when it enters the prism, once when it exits the prism. And light will therefore come out in several different directions. And why is that? Well, of course, because we know from Snell's law that the amount light is diffracted is dependent upon the wavelength of that particular light. So if we have a source with multiple wavelengths, then diffraction will cause the light to leave that prism at different angles. So what we do is we look through our telescope here that has crosshairs in it. We center those crosshairs on that narrow spectral line of light and read its measurement on the scale provided here on the instrument. Then we move the telescope to the next spectral line, record its position, and so on. So we do that for as many spectral lines as we can. In fact, for helium, the author says to find 8, but if you could only find 7, that's good enough. And I'll elaborate that in a moment. Let's see. Now, the direction that the outcoming light goes in is dependent upon the position of that prism. So one might ask, what does knowing the position of the light have to do with the wavelength if the light comes out of that prism at an arbitrary angle? Arbitrary insofar as it being totally dependent on how I position this prism. Well, here's how we go about determining the wavelength. In fact, let me put you on pause and back up this camera for a second. Oh, before I do that though, the light source here. We have 2 different bulbs. One of them is a helium source, one is a hydrogen source. This one in here happens to be a hydrogen bulb. So that is light coming from hydrogen atoms, the light in the center here. Now, of course, you only see one color. Ignore the endpoints. Although you only see one color, there are actually 4 there. And, well, obviously you don't see the 4 distinct colors because they're all blended in with each other. But that is, of course, the purpose of our prism, to separate those 4 different wavelengths of light into 4 different directions so we could view them separately. So let me put you on pause and back you up. So the question I posed was, if the location of our light from our source is arbitrary, depending upon the position of our prism, how do we know what its wavelength is? And this is what we do. We first use a source that is going to be considered our known source, and that's going to be helium. So we will use a helium light bulb and examine where the spectral lines from that bulb fall. We're going to measure 7 of them. And you know what? I mean, we could do this 100 times at arbitrary positions of this prism and get 100 different locations of those spectral lines. Here's the catch. We don't move it. We measure the location of those 7 spectral lines with helium. Then we simply swap out the bulb. We put in hydrogen without moving the prism. And those initial readings serve as our calibration curve, because what we'll do is we'll plot wavelength versus position, wavelength versus the angle reading we got from this instrument. And that is our known for each of those 7 different spectral lines, each of those 7 different colors. If you look in your lab manual, the wavelength is given to us. So we use that source to make this calibration curve, replace the bulb with a hydrogen source, and view the light, view the spectral lines from the hydrogen. Now, we take the angular position of those spectral lines we find. We're going to do it for 4. In fact, there are only 4 in the visible spectrum. Well, okay, so I lied. There may be, are there 4? I think there might be 5. It doesn't matter. We're going to do it for 4 and consult our graph. For any one of those given 4 spectral line locations from hydrogen, we'll get that angular displacement, find it in our graph, and then see what wavelength it pertains to. So helium is meant for us to produce a calibration curve, and then we'll investigate hydrogen and experimentally determine what the wavelengths of the 4 spectral lines of hydrogen are. And then, of course, from those wavelengths, we could determine the energy associated with those photons. And then you'll do some analysis on your own involving Bohr's model. But that is it. That's simply what we do. The challenging part was capturing this with a camera, and here's what I did. So, in fact, well, here's what I did. I found one of those spectral lines, and I simply just placed my cell phone up against this eyepiece, which wasn't an easy thing because it's very finicky. The margin of error, I mean, that thing has to be placed just perfect. And so I captured the best images that I could, plus I was doing this in the dark. But anyway, when you're looking through this eyepiece with the naked eye, you see a broad range, and you see spectral lines that are well defined and vertical. When I capture this with the camera, the view is somewhat more narrow. Also, some of those spectral lines are curved, and sometimes there's glare, which gives the appearance of an additional faint line that really isn't there. How does that affect us? It doesn't. It doesn't affect us at all, because whenever I found a spectral line, whenever I put my crosshairs on a spectral line, I photographed it, and on that photograph I put a little arrow as to the location of the crosshairs and a little notation to what color it pertained to. So you can easily just look at this photograph, consult your lab manual, and you immediately know what the wavelength is for that particular spectral line. This is for the helium, of course, for our known, for our standard. And after I took that picture, I then photographed the scale on this instrument. And I took two photographs. One of them is so that you could determine where the 0 tick mark on this sliding scale is. And the other photograph is a close-up of a position on the sliding scale of interest. And if you're kind of confused about that, you won't be. I'll elaborate on that in a few minutes. But anyway, there you go. For each spectral line, you have 3 photographs. Looking at the line through the telescope, through the eyepiece there, and then 2 photographs of the scale. Now, when students come into the lab to do this, okay, sometimes they don't read their lab manual ahead of time, so they don't really have a jump on how to read this vernier scale. Also, it's done in the dark, so it's kind of hard. There's a little magnifying glass here provided for the viewer to examine those tick marks because they're rather close together. But we don't need this because our camera acts as a magnifying glass. And we're going to avoid all those problems because I'm not in a dark room, and I take a nice picture of it and I provide that to you. But what I was saying is that a lot of times I'll see students reading this scale, kind of winging it, kind of guessing. And that's the worst thing you want to do for this lab. And that is because the range over which we see these spectral lines is very small. Off the top of my head, I don't recall. I'm going to guess like 5 degrees. So if we're measuring like 7 different spectral lines over the span of such a small space, and you're only guessing to the nearest half a degree, I mean, you're just introducing a tremendous amount of error when you finally do your graph. So it is important, for the sake of your analysis, for this data to be meaningful, to be able to read this instrument accurately. Now, with that said, I will provide a segment, like a little tutorial at the end of this video. Let's see, the author talks a little bit about it in the lab manual, but if you feel you want to go through it with me, just keep watching, because we've just about wrapped this up. I don't think that there's really anything else to talk about. This is a very straightforward lab as far as acquiring the data goes, and we've avoided all the pitfalls, working in the dark. When you turn on this source, technically it should be only turned on for 30 seconds and then turned off and let it cool off for 30 seconds. Then you could turn it back on, just to preserve the life of the bulb. The manufacturer suggests that you do that when you're using it. So there's it's not as easy or straightforward. There's a lot of little things that you gotta be mindful of, and again, you don't have to worry about any of that because you just need to look at the photographs. So that wraps up this segment, and I will see you next week. And again, if you want a quick tutorial, I think it's about 15 minutes long. Stay tuned, but see you next week. Oh, wait a minute. I knew I forgot something. I was going to elaborate on the 7 versus 8 spectral lines that the author asked you to find for our standard helium source. Now, in your lab manual, the author says, or lists 8 of the spectral lines and gives you their corresponding wavelengths and says to find 8. But one of them being hard to find, he goes ahead and says, finding 7 is fine. That if that's the only mountain you see, it's fine. So instead of me spending like an additional hour in here messing around with the prism and I don't want to go into what he said, 7 is what I found, and was done with it. Okay, so here's why I bring it up. When I'm doing my graph, my calibration curve, I plot those 7 spectral lines, the location, the wavelength versus location. Now I get my 4 spectral lines for our unknown sample, which is the helium, and I come to find that one of those spectral lines from hydrogen, our unknown, is not on our graph. It is towards my left, your right. It lies outside of the curve that I just plotted. So how do I determine the wavelength of that spectral line? I suppose that you can take an educated guess. I mean, it's pretty far off. Well, in fact, 2 were off, but one of them was so damn close that it almost didn't even matter. I was able to determine that wavelength very accurately. It's just a hair off of my calibration curve. But again, one of those is several degrees off, and this curve isn't a well-defined function, this calibration curve. So it would kind of be a guess. You're gonna have to guess what that wavelength is. When I did the analysis, what I did was just totally discarded it. I didn't even want to bother with it. I was a little disappointed. I was told that 7 would be fine, and it turns out it isn't really fine. So this I mean, is ultimately up to your instructor what you want to do with this info, whether or not you just want to analyze those 3 spectral lines or include that 4th one, which is going to be a guess. Now, with those 3 that I was able to, with those 2 spectral lines that I was able to find their wavelengths with my calibration curve, that info was enough to do all of the analysis in the data. I wasn't missing out on anything, so we'll leave that up to your instructor. And since I have you here, I'll flash a picture of what it looks like when I put the camera in front of the eyepiece. So there's going to be a picture flash right here. So that was an example of what your photographs, what some of your photographs will look like. And for real now, I'll see you next week, and enjoy the rest of the video if you choose to watch it. Ladies and gentlemen, what you're looking at is a close-up of our infamous vernier scale. And after this tutorial, I'm confident that you'll be able to read this very easily. It'll seem trivial. So let's go ahead and get started. First off, let me say that when I'm looking through the eyepiece of this instrument, there are 2 crosshairs in view. And what we do is we center those crosshairs on the object of interest, in this case a spectral line. Then after doing so, we take a look at this scale and see what its angular position is. So let's say I do indeed have the crosshairs centered on a spectral line, and I want to determine its position. The first thing you do is notice where the 0 tick mark on this sliding scale is located. By the way, this is our sliding scale and this is our main scale. The sliding scale is, for obvious reasons, called a sliding scale. And our main scale gives us the number of degrees. So you'll see that they're labeled every 10 degrees, 130, 140, 150. Furthermore, you'll see that in the span of 10 degrees, there are 20 tick marks. So let me zoom in on those for a second. And let me distinguish the two types of tick marks that those represent. I will call this larger tick mark a main tick mark and this smaller tick mark a minor tick mark. So in the span of 10 degrees, I have 10 of these major tick marks along with 10 of these minor tick marks. These major tick marks indicate degrees. So this is 140 degrees, 141, 142, 143, and so on. In fact, if this 0 tick mark on the sliding scale was positioned directly above that tick mark there, I would know that my measurement is 142 degrees. Likewise, this would be 145 degrees. So that's very straightforward. Now let's just say that our 0 fell on one of these minor tick marks. So intuitively, what you would think is that this would give a reading of, I'm trying to position my pointer here. Okay, you would think that this is what? 141, 142, 143. You would think that this is 143.5 degrees. Now, okay, so technically you'd be right, but that's not really how this instrument is designed. That minor tick mark doesn't represent a fifth, 0.5 degrees. It represents 30 minutes. So keep this in mind. There are 60 minutes and 1 degrees. And that minor tick mark represents 30 minutes. So the correct reading of this particular measurement would be 43 degrees and 30 minutes. So of course this would be 44 degrees. This right here would be 44 degrees, 30 minutes. This is 45 degrees, 30 minutes, and so on. So let us suppose that our 0 tick mark on the sliding scale here fell, say, somewhere between 140 degrees and 140 degrees and 30 minutes. Our job is to determine how many minutes beyond 140 degrees are we? And that is done relatively simple. But let me say a few words about this scale first. If you notice, in the distance between 0 and 30 on our sliding scale, there are 30 tick marks. Now, let me, for the sake of explanation, put that 0 tick mark on from the sliding scale dead center on 140. Okay, so again, the sliding scale has 30 tick marks in the span of this distance to that distance. In the same corresponding distance from here to here on the main scale, there are actually only 29 tick marks. I mean, we could count them. From 140 to 150, that's 20 tick marks on the main scale. Then we have 22, 24, 26, 28, 29. So there are only 29 tick marks in that space on the main scale, but there are 30 tick marks in that same amount of space on the sliding scale. So the reason I bring this to your attention is because that is the whole premise on how this operates. Because there is one fewer tick mark on the main scale, that means that one and only one of the tick marks on this sliding scale can align perfectly with the tick mark on the main scale. So what our job is when we are reading this, if this 0 tick mark does indeed fall somewhere midway between a degree and 30 minutes, our job is to determine exactly how many minutes away from this mark are we. So I know my reading in this case here is larger than 140 degrees, but smaller than 140 degrees and 30 minutes. Well, how many minutes away are we from 140 degrees? What we do simply is determine which one of the tick marks on this sliding scale aligns with the tick mark on the main scale. So I'll zoom in on this, and I can see that it is, I wish I could zoom in on it a little more, but you'll have to agree that it is this tick mark here. Now, you may think it's this tick mark here, but that is just from parallax due to the position of the camera. It is this one right here. So which tick mark on this sliding scale does that pertain to? Well, the 22 tick mark. And these tick marks here indicate minutes. So we are at the 22-minute mark. So if I go back to the position of our 0, I'll find that my measurement reading is 140 degrees and 22 minutes. By the way, when you saw me rotate this, I'm rotating like the whole instrument. I'm not messing around with the position of the eyepiece. And that's just so that we could view the different region of that scale better. So hopefully that's clear to you. It's rather basic. Let's try another measurement. Let's say that we are at that position right there. So from the main scale, I see that I'm above 142 degrees, but less than 142 and 30 minutes. So how many minutes am I beyond 142 degrees? Well, let's take a look and see if we could find those two aligned tick marks. And I'm going to move it slightly this way. From my view here, it appears to be this one right there, which corresponds to 14 minutes. 4 tick marks beyond this 10. So this is 14 minutes, and my reading then becomes 142 degrees and 14 minutes. So a logical question you may be asking is that if there are indeed 60 minutes in 1 degree, how are you able to determine minutes beyond 30 if this only has 30 tick marks? And again, that is simple, and here's how. If that 0 was, let's say, in that region there, this is how you'd go about reading it. You are 140 degrees, well, you are beyond 140 degrees 30 minutes, but not quite at 141 degrees. In other words, you are some amount of minutes beyond 140 degrees 30 minutes, and we want to determine how many minutes past this 30-minute mark are we. So let's go ahead and figure that out. Let me zoom in a bit. It appears to be this one right here. This tick mark on the sliding scale aligns with this tick mark on the main scale, so I want to focus on this tick mark, and that one indeed represents 17 minutes. So what is my final reading? It is 140 degrees plus 30 minutes plus 17 minutes. So 30 plus 17 is 47, so I am at 140 degrees plus 47 minutes. So basically what we've just discovered is that whenever you're looking at the position of this 0 tick mark on the sliding scale, you want to be mindful of where it falls in regards to beyond this 30-minute mark or not quite reaching it yet. So if we were to put this at an arbitrary location, half the time we would be in between this, we would be in between a major tick mark and a minor tick mark. So we just need to know how many minutes there are on this sliding scale and add that to whatever tick mark this represents in terms of degrees. And the other half of the time we would be beyond that 30-minute mark. So we would read the minutes on this sliding scale and keep in mind, or we would have to remember to add 30 minutes to it. The last thing I want to bring to your attention is sometimes it's difficult to determine which tick mark most closely aligns from the sliding scale and the main scale, which tick marks align the best. Sometimes it could be a toss-up between two. You know, based on that, the uncertainty in this measurement is plus or minus 1 minute. When I was measuring for our angles, the ones provided in your data sheet, I don't think that I really had that problem. I mean, if you really zoom in on it, there's a best fit for just the alignment of one particular tick mark. But anyway, if this camera is positioned like at a slightly different angle, you could see how that would introduce a tremendous amount of inaccuracy. So what I did when I photographed this scale for you in your data sheet, I positioned the lens of this camera in the right above the proximity of the sliding scale's tick mark of interest, so that parallax does not play a role in your ability to read these measurements correctly based on those photographs. So let me think real fast. Did I cover everything? Yes, I think I did. So with that, I really think that you're going to get great results. I've already done the analysis, and I found that if done correctly, yes, your experimental error is incredibly small. Ultimately, I guess it has to do with your graphing ability, whether or not you do it by hand as the lab manual instructs, or if you do it with software. Although if you do it on something like Excel, I don't know how well. Well, I'm just gonna shut up now. The curve that you get doesn't necessarily follow a specific straightforward function to do a curve fit fitting on. So I mean, I was able to do it with my software. I don't know that Excel offers that same feature, but anyhow, take your time with these measurements. So in your final analysis, you'll know that your measurements are right on dead spot, great measurements, and that won't play a factor in your error. If anything, it'll just be your graph. So have fun with it, good luck, and I shall see you next week.